Let's come back to talk about filter defining modules. So firstly, one thing we didn't really mention is that given let's say filter vector space, how do you define the due object? The key point is how do you define the filtration of the due point on the due object, right? So recall in the filtered, the category filtered character spaces, we have the following objects. Firstly, tensor product. If you have D1, D2, two objects in the filtered K-vector space, then we define a tensor product of these two, still a filtered key space as follows. Firstly, let's tell what is the structure as K-vector space. So this tensor product of filtered K space is defined to be as a K-vector space, just tensor product over K. Secondly, the filtration on tensor product is, as you could imagine, the filtration on each part. But then, how do you define I? I is when you take I1 plus I2 equals I. Second object, the unit object. Denote by K0. As K-vector space is K itself. And the filtration when I is less equal than 0, it's totally K. When I increase, it shrink, right? And we define for I starting from minus from 1 become 0. Canonically, this object, the reason we call it unit object is because its tensor product is isomorphic to D as filtered module. For any object in this category. Lastly, the key point of what we are recalling is the due object. The reason we talk about due object is because later we are going to do exercise to compute the Hodge number of the due. So the due object, of course, to compute the Hodge number, you have to really know the information about filtration. This is really by our convention, how to define the filtration on the DU. Of course, it should satisfy something, not. I mean, we define the filtration in order to satisfy something. So here, basically, we define the filtration in a way that we have to make sure the unit object DU is isomorphic to itself. So DU object denoted by DDU of an object D, this category, is defined as DDU equals home k du from D to K. As K vector space. With fill I d du defined to be fill minus I plus 1 d orthogonal. What that this symbol means? It means all those K linear maps, when you restricted it on this filtration, minus I plus 1D, because this is a submodule of D, right, equals 0. Among those K linear maps depend on D, those who vanish on this. And you could imagine when you increase your index I, this filtration of D becomes smaller and smaller. But then the requirement or the condition that this function restricted on this smaller and smaller one becomes 0. It's indicating that it could be bigger and bigger. That's why basically we'll see a phenomenon that if the jumping index for D is I, then the jumping index for DDU is minus I. Remark for this condition is that the reason we use strangely fill 1 minus I of D rather than fill minus I of D is to ensure that the DU of K0 is still K0 the unit object. I think we can take an example. So let's take an example. For example, if you have D equals K and then you have some filtration, let's say fill 1 equals K but fill 0 equals 0. And then this means for all the others it's always K, and then for the latter it is always 0. Right, give you the filtration information. And then now let's look at the DDU. So fill, let's say start with 1. Fill 1 of DDU by our formula given. And the definition is fill 0 D orthogonal, which means those F such that F restricted to fill 0 of D equals 0, but fill 0 of D is 0. Those F such F restricted to 0 is 0. So this is totally all of DDU. Now let's look at fill 0 of the due. This is those by the formula tells it's minus I plus 1, or 1 minus I. 1 minus I. Field 1 of the orthogonal consists of those f such that f restricted to field 1 of D is 0. Field 1 of D is K. Then this is, when you restrict to K0, you're totally 0. And then what is minus 1 ddu? This is 1 minus I field 2 d due those will vanish on the bigger the index, the smaller it is, right? For filtration of D. Wait, am I using am I make mistake on direction? So generally for filtration, when you're increasing your index, you're becoming smaller, right? Which means I should do this. So field 0, field 1, field 2, field 3, etc. So I'm going to modify this, I'm sorry. So field 0, accordingly this is K. So this is totally 0. Field 1, this is smaller, still K. And then field minus 1, this is 2, even smaller, becomes 0, right? Because field 2 D, this is 0. And so this is all D due. And you say for D due, when the index is dropping, it is becoming bigger, and so this is the same result, the same phenomenon. So field minus I of D due is D due, and then field 0 of D due is 0, and then everything later becomes 0, and bigger will become D due, because this is one dimensional. Because we are assuming D equals K, sorry, that's one dimension in this example. Okay, do you see the phenomenon? And so let's see the jumping index. Jump from 0, jump from the whole space to 0 is here. So jumping is -1 position, but here the jumping position from everything to 0 is 1. You see the phenomenon, right? This could be seen more directly, but it's enough for us to just observe this. And now let's go back to the exercise today. What we're going to do is we are going to prove some formulas. We are already done for Newton formula, but here let's look at for Hodge number, for the Newton number, for the Hodge number exercise today. So this is, you can also think of it as a proposition. So first part of the exercise, given short exact sequence of filtered p-space, filtered k-vector spaces, 0, D prime, D double prime, 0. We have the Hodge number of the middle equals the summation of two sides. It's additivity of Hodge number. So let's prove this. We have this isomorphism of K vector spaces. So we know that the filtration of d double prime is defined to be actually the ice filtration. It comes from the ice filtration of D quotient by the ice filtration of D prime. Actually, how do you define the filtration of D prime? The filtration of D prime, recall, this is just D intersection with D prime intersection with filtration of D. And you could think of this as definition of the filtration of D double prime. It comes from the quotient filtration. So for any integer, we have this. Now, what we care about is, recall, our formula is Hodge number of D equals all the integer I times the dimension of the graded ice graded piece as K vector space. So we're going to compute this, right? So K dimension of the graded piece I of D double prime is hence the dimension of D, the dimension of the graded piece of D minus the dimension of the graded piece of D double of D prime. And then again, using this formula, this is telling us the Hodge number of D equals the Hodge number of D prime plus the Hodge number of D double prime. Secondly, talking about the tensor product, right? Hodge number of the tensor product. The second exercise, take two filtered vector space, then prove that Hodge number of the tensor equals dimension D2 times Hodge number of D1 plus dimension D1 times Hodge number of D2. Particular tensor R times dimension K dimension minus 1 times TH D by iteration. Prove this. So this involves to again compute dimension of the graded piece of the tensor product. So recall the filtration of the tensor is defined to be I1 plus I2 equals I, and then you take the field I1 of D1 tensor field I2 D2. And now suppose jump position D1 and D2 to be G1, G2, GS, respectively M1, M2, MT. So what are the jumps position for the tensor product? It would be J1 plus M1. I mean, all the possible combination of pairs that give me different integer. Like the two sides, G1 plus M1 is the smallest, GS plus MT the biggest, but in the middle, I think it's possible some give you the same summation for different alpha, beta, and they give you the same jump position. Anyway, we could write th of the tensor equals let me think. Let me first write it this way. For alpha from 1 to S, beta from 1 to T, I'm just running over all the possible combinations of G alpha plus M beta. I mean, this is possible less equal, but it should not be a problem. Dimensions graded piece G alpha plus N beta D1 tensor D2 over K. Take them further equals summation Gm integers G plus N dimension of K graded piece of G plus N D1 tensor D2 over K. Right. question is, would it be a problem if, let's say, for example, J2 plus M3 equals G3 plus M2? And in that case, it would tell you feel J2 plus M3 of the tensor, actually it equals feel J2 D1 tensor feel M3 D2 plus feel G3 D1 tensor feel M2 D2. This case, and we compute the graded piece of J2 plus M3 of D1 tensor D2. And then compute the dimension of this, and then multiply by J2 plus M3. Then it doesn't matter. Well, we don't really care how it looks like on the right hand side, right? I mean, when there are repetition, you just remove it. You just remove it. I mean, right? It's like this. You just remove it. Wait. Or we should count it twice. So let's put a postpone here for a while. Let's continue. Let's continue to compute this. How do you compute this? Now observe that dimension graded piece J plus M D1 tensor D2 equals dimension graded piece J D1 times dimension K of the graded piece M times D2. Okay, if you want to use this formula, if we want to use this formula, then of course we have to compute it twice, and it doesn't matter. Really what you're doing is like, okay, I take 2 plus 3 and then 3 plus 2, but it corresponds to the same dimension here, but you have to compute it twice. It's really because here you have two terms give you the similar condition. But when you use this formula, the first term you compute is graded 2 of D1, graded 3 of D2, but the second is graded 3 of D1, graded 2 of D2. So you really have to count it twice. So which means it doesn't matter, it doesn't matter it coincides or not. You just write it down. These two never coincide, but the others possibly. It doesn't matter. We count it twice, which means even if G plus M is the same, but we count it twice if it's different G and M. Good. Therefore, TH of D1 tensor D2 over K equals addition G plus N times dimension graded J of D1 times dimension graded M D2. So this equals J times dimension graded piece J D1 times and integer dimension graded piece of M T2 plus and we'll just write that one term into two terms. J in Z graded piece M of D1 and then graded piece J of D2. So we separate into two parts. The first part is j times something. So what are the possible j times something? J times with whatever m. And so you fix the j, you have to collect all the m. And the other part is m times something. When m is fixed, again, it have to run over all the possible j. So got it into parts. And then this is dynamic, this is just d2 dimension. Dimension of all the graded pieces, dimension of d2 times can move this outside because there is no m. So the first parenthesis gives you exactly t Hodge number of d1 plus dimension of d1 over k times Hodge number of d2. We are done. Okay. Lastly, the last exercise to prove that if D is filtered character space, let's say more than that, filtered phi n module, such that finite dimension as KZ vector space. Frobenius is bijective. Then we claim the Hodge number of its due equal to minus the Hodge number of D proof. Here I didn't see where did we use the fact it has a monodromy operator structure. So just by general theory about dual vector space, we have the exterior power of du equals the du of the exterior power. So dk is, say, this changes to k. Therefore, just by considering the one-dimensional case, despite what we discussed at the beginning, so the filtration of the du, basically the jumping position changed the sign. Okay.